All right. Oh, good afternoon, everybody. So we continue our adventures into digital logic. The first part of the course here, a lot of you may or may not have seen parts of this because, codes you might have seen in computer science and things like that. We're going to go a little bit deeper, like I've been mentioning. The main thing we want you to do is not just to learn the algorithms. The whole purpose is you're learning these so you can think, how do I build a circuit to do them? So we need you to know it at a certain depth level. So when we introduce the second half of this, which is how do you turn these type of systems into an algorithm, basically into hardware, you can kind of translate it. And this process really becomes kind of fundamental to us. And if you've taken a computer science course already, you've kind of seen you can take an algorithm, a sequence of steps to solve a problem, and you can turn it into code. Well, everything you could do turning into code, you can also turn into hardware. Okay, so really, if you think about it, if you understand the idea of algorithms and how to translate them, you could do either computer science or computer engineering. It just depends, do you implement it to code or do you implement it to hardware? And if you can keep that idea in your head that it could go either way, and you're just kind of learning how do you translate it into these different ways of describing them, you'll be able to do anything. And that's really what we want, is maximum flexibility. All right, so today's goal is to teach you about basically other important codes that are out there. There is no way on this planet I can cover all the codes. Right? And even if I could, it would be a useless waste of your brain. There are some codes that are kind of important and you want to understand the idea behind them. So that's what we're going to spend our time on doing. Particular importance today will be gray codes. We'll use those quite a bit. And we'll talk about ASCII codes, because ASCII codes become really important, even if you're using like Unicode and stuff like that to be able to do it. ASCII code is the basis of Unicode. So, it's still embedded within there. So this idea, and it allows us to introduce another idea called parity. And then we'll talk about a few other kind of specialty codes that will come up for useful areas. I'm going to start off with gray codes. How many people have heard of gray codes before? Okay. So here's the basic scenario with a gray code, or at least one good way to think about it. It's a mathematical entity, but there's a practical area. So imagine for a sec I'm taking in data from the physical world. Okay? One scenario could be, imagine I've got some NC mill, so I've got some type of a device here, whatever it is, that's going to spin a shaft. So we've got coming off of this a shaft. Right, imagine that wasn't there. I'm not claiming to be an artist. I've got a spinning shaft on it. And I want to know how fast that shaft is spinning. Or maybe even you could imagine the same type of thing. I got a wheel and I want to know where the wheel position is by watching the axle or something. Now, one thing I might want to do to try to figure this out is kind of imagine I put a light above it that's shining light down. It reflects off, and I've got some type of a detector. All right, so I got a light and a detector, and it bounces it off. And then I could put encoding bars on it, right? Light and dark passages or sections on this. And as it spins, you'll see light, dark, light, dark, light, dark, right? So you could read them. And you can imagine I could put a bunch of these down the shaft, so I could even number the positions. If you just wanted to know how fast it's going, you just want to see the light, dark passages. If you wanted to know a number, I could put digits, right? First digit here and second digit on the next one, right? And just basically have a series of digit bands going around here that have light, dark patterns. Now, you could say, hey, if I did that, I could put binary. Right? If I have 4 positions, all I'd need is 4 different numbers for there. I could do 0, 0, 0, 1, 1, 0, 1, 1. Right? I'd have 4 different numbers, and I could tell which quadrant I was in. Because each of these quadrants around the outside, I could print, right? A 0, let's say, is I don't fill in the box, and a 1 means I fill it in. So I could have 0, 0. I don't fill either. Right? The next quadrant I could have 0, 1. Right? So it's right. So I've got 0, 0, 0, 1. Right? Similarly going around, I could fill those in. I could have 2 lights. It reads each of those. I could just read my digits. Sounds reasonable, right? Well, my pattern then would be in binary 0, 0, 0, 1, 1, 0, 1, 1. Sounds great, but what happens if there's a slight skew to my lights? Instead of perfectly reading at the same spot, what if one of them was slightly off? So that maybe this one ended up reading from here and this one read a little bit from the back. All right? Well, what you would see as you kind of passed around, if I were to take these and flatten them out, you would see, right, the 0, and I'd see these parentheses. Right, 0, 0, 0, 1, this would be filled in. Right, then I'd have 1, 0, and then 1, 1. Right? And if I'm reading it, so I'm reading here and here, as I move down, I definitely see 0, 0, no problems. Right? Notice as I start moving down, I see a 0, 0. I see a 0, 1. That sounds fine. But then what do I see? A 1, 1. And then I see a 1, 0. Right? You can imagine as it kind of carries around. But before I see 1, 1, I see 1, 1 before I should have seen 1, 1. If they're a little bit out of skew in orientation, I read it the wrong way. A similar problem can happen if I twist them in the other direction. I can also get out of order numbers. Right? That's kind of potentially problematic and dangerous, because think if you've got some type of an environment, this is like reading a wheel. How likely is that linear thing to get bumped sometime and not be perfectly angled right? And then do you want to be reading garbage data, right, and have junk come around pretty often? Right? That's not a very what we call robust, right? It works perfectly if everything's great, but anything goes wrong and it falls apart. That's a horrible situation, right? We don't want situations that create problems like that. This is what gray code handles, right? And the reason why you get a problem here, notice I didn't have a problem here where 1 turned on. There was no difficulty. But right here is where I had my problem. That's because 2-bit switch. The problem is when you have 2-bit switch, which one switches first? Does the one on the left switch before the one on the right? Right? If the one on the left switches before the one on the right, I could go back from 0, 1 to 0, 0 again. If they go simultaneously, I get exactly what I want. And if the one on the right switches first, I can get that 1, 1 insertion. But the problems only occur where 2 or more bits switch at the same time. We call this a race. Right? These are called race conditions, whenever 2 things could happen at the same time. And it's almost impossible for race conditions like this to have 2 runners and they end at the exact same time. Okay? That'd be the perfect world, but that ain't what happens in real life. Okay? So gray code just makes sure there's only 1 bit flip at a time. Right? This is how it avoids the whole trouble. It just doesn't put a situation where 2 bits are racing against each other. So it doesn't matter if it gets bent a little or something. The code itself only has 1 bit flip, and 1 bit flip cannot happen out of sequence because there's only one thing that's happening. So it doesn't matter what order. It's the only thing that's going on. It's kind of like if you're the only person in a race, I can tell you you win, right? There's no threat to the order until you add a second one. Make sense? This is the whole idea. So when you're dealing with things in the physical world, they can almost always get messed up. And it's almost always because of these race conditions. So what we want to do is remove the races. We want to make sure that's an absolute guarantee what the order happens. Does that make sense? The question is, how do we do that? But first off is the motivation. Do you understand the problem and where it creeps up? Awesome. All right, so let's talk about how gray code achieves this 1 bit flip at a time. All right. So if I only have one bit, it's pretty easy to do, right? 0, 1, 0, 1. Imagine I want to add a second bit flip in. All right, now, trivially, I can make these both zeros. All right? And once I've used these zeros up, I've only got 0 and 1 for each one of these. I have to switch to 1. So I have no choice on this side. But if I'm having this bit flip, I can't let this one flip. So I have to hold this one. So of my combinations, I have to go in this sequence. Does that make sense? This is just necessity, starting from a single bit flip. All right? I just go, oh, 0 and 1 is my only two things. I'm adding in a new thing. I might as well just both call them 0. I mean, you could call them both 1, but why? It doesn't really help you any. Right? So since the other digit has to be pretty much 0, its flip must occur. There's only 4 possibilities. Half have to be 0, half have to be 1. It's just where do you put them? We don't want weird splits. What we did before, 0, 1, 0, 1, right? There's 2 regions where there's 0, 1s. This one, if you think about, if I cut this out and wrapped it around in a circle, I would have a 0, 0, 1, 1 region. And then when I'm coming around here, right, 0, 1, 1, 0, it wraps up 0. Right, so all the zeros are kind of in a band and all the ones are in a band. It's grouping them together. Does that make sense? So we're trying to group things together a little bit better. Now, if you watch, this is 2 bits. And notice from any one transition, 1 bit flips. Here, 1 bit flips. And then here, 1 bit flips. And then from this one up, that bit flips. Never more than 1 bit flip. Now, think about how we did this. Right? When we added an extra bit, we just put that bit. Everything that was here, we put all zeros. So I'm going to follow that to the next bit. I add another bit. I put all zeros next to the pattern I have. And then what I did was the next half, I have all 1s. Right? Because this was a length of 4, so I put 4 zeros. I put 4 1s. In this case, I put 2 zeros and then 2 1s. And then I took the other pattern that was there and I mirrored it. So I'm going to do that same thing. I'm going to mirror this one. So 1, 1 has to go closest, 0, 0 farthest. And I mirror this one. 0 comes down here, 1 comes here, 1 comes here, 0 comes here. All right? So notice we started off, we flipped, and we wrote in our 0, 1, 1. We've got our next section. This whole thing flips. Right? And we wrote zeros, all zeros and then all 1s. That pattern is the pattern you build up a gray code. Does that make sense? You'll do that all, I mean, you can make as many bits as you want. Now I've got 8. I can put all zeros here, and then 8 1s, and then I take this whole block and I mirror it down. Good? All right. So think about these codes here, right? This is 0, 1. That's normal just to binary now. But now this one is 2, 0, 1, 1. So they do not have the place value system that our normal binary does. The place value system is gone. So we came up with regular binary, so it was really good for calculating things. It was basically one of our math systems. And that's where binary excels, is in doing calculations. But we found a need for something else, right? So this one is 3, 0, 1, 0, which would have been 2. Right? This, which we would have thought of as 6, in gray code is 4. Right? So this is 5, 6, and 7 in gray code. Does that make sense? And you can notice on any one of these, doesn't matter which one you do, take a look at 4 to 5. Right? Only 1 bit flips. The other ones stay the same. You can pick whatever you want. 6 to 7, only 1 bit flips. 5 to 6, 1 bit flips. The other ones stay the same. So if you were doing that same slightly skewed reader, you would have no problems. It will give you the correct code sequence. Okay, does that make sense? That's its real big benefit, right, from the outside. It will generate a second big benefit for us that's related to this. This is a sequence that makes it really hard to get errors. It kind of pulls all the errors, all the easy flips together and groups them so it's easy to see. So when we get to our design methodologies, our biggest design methodology we're going to do called Carnot maps are going to use this gray code sequencing to place things in to try to do circuit design. Because what we're going to do is every one of our input signals flipping, we're only going to want to allow one to flip at a time so we can reduce errors in our circuits. So we'll use the gray codes at that point, or at least a gray code ordering. We'll allow you to use whatever number interpretation you want. But we'll list whatever your number you want in this sequence because it will allow us to just take a look at one flip at a time. Think of it this way. If you're looking for a problem, it's easier to go through and check individual things rather than looking for a whole bunch of stuff checking at once to look for problems. And so that's what we're going to do for our design things to try to remove errors. So it will utilize this gray code also. Okay, so let me take a look at these, right? We've got, let me write these ones down, right? 0, 0, 0, 0, 0, 1, 0, 1, 1, right? 1, 0, 1, 1, 0, 1, 1, 1, 0, 1, 1, 0, 0. That's gray code in 3 bits. Now the question is there a way looking at one of these? Like imagine you got one of these codes, 1, 1, 1, right? And you want to find out what was its value in binary. Is there a way to kind of rapidly switch between binary and gray code? And it turns out there are some nice fast ways to go between them. And to see that, I want to kind of put this is our gray and here's our binary. We'll just do 3 bits. I might group them just so it's kind of easier to compare. Okay. Now, take a look at both gray code and binary code. Look at their most significant digits. Notice anything? The most significant bit, the leftmost bit, is identical. So this is going to suggest, since they're both identical, they're not identical on any of the other bits. This would kind of suggest if we're going to transfer from one to the other, it's best to do it by copying the leftmost bit, and we'll move left to right through our sequence. Okay. Now, take a look when we go to our next bit. Let's imagine, I wanted to take a binary and I wanted to go to a gray code. Okay? Now, when we're taking a look at binary to gray code, we're going to take this and we look and we go, okay, these are all zeros, right? Here's 0, 0, 1, 1, 0, 0, 1, 1. So far, so good. All right? These are all ones, but these are flipped if I'm going from here to here. All right? So it looks like if they're all zeros here, then I should just copy the next bit. All right? Ones, I'm flipping the next bit. Let's see if that pattern holds. The zeros, I copy. Ones, 0, 1, 1, 0, I flip. See how that works? These are ones, so I would flip these bits. These are ones, I would flip them. These are both ones, so I should flip these two. 0, 1 should become 1, 0, and it does. See how that goes? So when we're going this direction to this, right, we copy the first bit. And then if the bit to my left of my digit, if the bit is a 0, I will copy. If it's a 1, I will flip it. That's basically the rule. So consider one of these numbers. Like, let's say we took 3 in binary. Right? So this is binary to gray code. So if I followed this rule, right, my binary number 3, I want to go to grade, so I'm going to copy the first bit, 0. I look at the next bit. The bit to its left is a 0, so I'm going to copy it. The bit to the left is a 0, so I will copy it, 0, 1. I look at the next bit. The bit to its left is a 1, so I'm going to flip the bit. So 1 becomes a 0. So this is my binary. This should be my gray code. So if I look up 0, 1, 0 in gray code, I see it's the number 3. Right? And we know in binary 0, 1, 1 is 3. So that took 3 in binary to 3 in gray code by this pattern. Does that make sense? Everybody's like, ooh, super quiet, right? I mean, I could decide to be like, great, what if I ask you to do, 1, 0, 1, 1, 0, 1, 1, 0, right? If I want to take this from binary, and let's say it's just truly in binary, it's not 1's complement or anything like that, it's just binary. If I wanted to take this number and turn it into a gray code, I would follow this exact pattern. I would take this and I would go 1, and I take the next bit. The bit to its left is a 1, so I'm going to flip it. Go to the next one. The bit to its left is a 0, so I copy. This one, all right, the bit to its left is a 1, so I flip. This one, the bit to its left is a 1, so I flip. This one, bit to the left is a 0, so I copy. This one, bit to the left is a 1, so I flip it. And this one, the bit to the left is a 1, so I flip it. And this would be the gray code. Works real nice and easy. Okay? That pattern would be fairly easy to do inside of a circuit. And we'll deal with this later, but this flip or not flip on a 0 or a 1 is called an exclusive OR gate. We'll get to it later, but it's a single gate that will do exactly this functionality. Okay? So we can see this is a nice, easy conversion method. We feel comfy with that part. Okay. Let's take this same thing. I want to recopy this whole table. Let's consider going the other direction. Should it be the same? Yeah, I see some people say, no, it's not guaranteed to be the same. And in particular, it's not going to be the same. An easy one to spot this on is notice what goes on here. Right? If I were to do that same pattern to go from gray code to binary, I copy the 1, yay, that works. Right? The bit to the left is a 1, so I flip it, yay, that works. Look at the next one, 0, the bit to the left is a 0, I should copy it. Uh-oh. That didn't work. Okay? So the first part is true though, right? I'll do the same thing here, which is copy the first bit. Oops, started writing first bit. Copy the first bit. Starting from the left again, just note that. Now, this one's going to take a little bit more work. We're going to create what's sometimes called a mask bit. So we're going to say our mask is going to be equal to the first bit. And then, right, we haven't said what we're going to do with it. This just kind of sets it up. This is going to take the place of our look to your left, right? Because now everything to the left has a cumulative effect. So we have to have something that's going to kind of hold the overall effect. So now what we're going to do is we're going to do that same, flip or don't, but we're going to say if the mask is 0, then we will copy. 1, we will flip. And not only will we copy that bit, right, but if it was a 0, we copy and the mask stays. If we flip, the mask flips also. That make sense? Okay, so let's consider this addition, right? So this mask is now holding kind of the cumulative effect of how many ones have you seen already, really? That's what it's asking. Have you seen an even number of ones or an odd number of ones? If there's an odd number of ones to your left, then you're flipping. If it's an even number, you're copying. So it just has that kind of cumulative effect of counting all the ones. That's all the mask is really doing for you. But take a look at this one here when we're converting, right? So let's consider 1, 0, 0 in gray code. And we'll add a mask here. So step 1, we're going to copy this 1 down. And that sets our mask to 1. Make sense? First step. Well, actually 1 and 2. We copied the first bit down, and we set the mask equal to the first bit. Let me just do this in color so it's a little bit easier to see that. Now we take a look at the next bit. All right? We take a look at the mask. If the mask is a 1, then we're going to flip. Right? Actually, I should say this. So this is if the mask, and this is if the bit that I'm dealing with. Because we've got to count our bit. If the bit is a 0 and the bit is a 1. I just clarify on that one. All right? So this is checking the mask. This side has to check the bit that we're flipping. So in this case, it's a 0 that I'm taking. And the mask is a 1. So the mask is a 1, so I have to flip the bit. But the bit was a 0, so the mask stays. Does that make sense? So only when I encounter a bit that's a 1 will the mask flip. So the mask is controlled by the bit, and the bit conversion is controlled by the mask. So, and this, it stays, because the bit was a 0. So it stays a 1. The next one, I want to take this bit, so I check the mask. The mask is still a 1. It hasn't changed, because there's only one 1 to my left. All right, remember, the mask is telling me how many 1s to my left, even or odd. It's odd. It's a 1, so I'm going to flip. This bit is a 0, though, so the mask stays. So the mask still ends up a 1. So 1, 0, 0 becomes 1, 1, 1. Let's try one that's a little bit kind of uglier that has multiple 1s on this side. All right, let's consider the 1, 1, 1 going back. All right, so this 1, 1, 1, remember this is my number 5. I want to see, do I get 5 in binary? Let me stick with my blue and then the green red. So 1, 1, 1 in gray code. And we'll have our initial mask. All right. First bit, no matter what, you copy it down, and that becomes the mask. The next one. The mask is a 1, so I'm in flip mode. So I'm going to flip the bit. The bit was a 1, though. And if the bit is a 1, the mask also flips. Make sense? I now go to the next digit. I want to deal with this one. My mask is a 0, so I copy. But the bit was a 1, so my mask flips. And it says 111 goes to 101. 5 in gray code becomes 5 in binary. That's the whole idea of the mask and the flip conversions. Okay? And again, this is just, there's a memory in the circuit now to remember these. But we'll be able to use those XORs in the second half of the class we get into memory. You could build this as a pretty straightforward circuit to convert. And those circuits have to be built when you take inputs that are coming in on gray code, which is a little more reliable, but you want to convert it into binary. So this gray to binary conversion has to go. If we want to go the other way to make sure it's ensured, you know, hey, move to this position, you're counting your numbers off in binary, you got to convert it to gray to go outside. Does that make sense? Okay, everybody good? Was that a question? Okay. All right. So if we feel comfy with this, this is the big things I want you to get about gray code. We talked about how to build it, right? Every time you build it, right, we just start out with 0, 1. When you add the new digits in, you just put all zeros next to whatever your pattern was, add equal number of ones down, and flip the pattern you had. I go from, 2 bits, which has that 4 pattern, I put all zeros next to it, all ones, and I flipped them in their sequencing. But their position keeps keeping their value. All right, so this just gives you what the new position values are for them. If you look on robotic stuff, like on wheels, wheel encoders for robot cars or other types of stuff, it is gray code that is on them. So if you ever look at those and wonder why the patterns are on gray code, because that way if you tape them on or it gets skewed a little, it doesn't screw up your robot's read for position sensing. All right, we good? Cool, and we know quick ways to convert between them. All right, so that's dealing with gray codes. Okay, red's not a great one to read. Green's got a nice peaceful color. Let's go with green. All right, let's talk about some other codes that are out there before we jump to dealing with ASCII. And there are tons of codes out there. I'm not going to attempt to deal with all of them, but some of them have some nice features to them. Right? We've considered our binary. Just consider binary for 4 bits. The position values are 4, 2, 1, and 0, right? So, oops. Sorry, for 4 bits, I could have, 8, 4, 2, 1, right? That's the 1's digit, the 2's digit, the 4 digit, the 8's digit. Let's consider I only want to do decimal, right? So I would only need 10 of the numbers that are in here, right? So I could have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. I don't need the other ones. That's as far as I have to go. Now, one of the things we mentioned we want to do on things was we often want to take these complements that are relative to our radix or our base. Okay? Now, remember when we were doing 2's complement, to get 1's complement, we just flipped all the bits. And then we added 1 to get 2's complement. Well, if I'm dealing with decimal here, I could just use these codes to make what's called binary coded decimal. And this is actually BCD right here. So if you ever hear people talk about BCD, this is what they mean. The other codes are illegal. Okay? Now, but imagine I wanted to get the 10's complement because I want to do subtraction nicely. In order to get the 10's complement, I got to do the 9's complement, and then I have to add 1. Well, the 9's complement is basically 9 minus this number. Right? So what might be kind of nice is if to get the 9's complement, I could just take and just flip my relative bits here to get my, the reverse of what I want, or the flip of it, right? And so that would create kind of a nice situation that's in here. It'd be kind of neat if I could extend it the whole way and everything else, but consider some possibilities that are in here. Right? If you look at this, and I considered just some subset of this, for instance. Like, for instance, let's, if you look at any one of these, and I just flip the bits, right? 1, and I got 0, 0, 1, I end up with 9. And 9 plus 6 gives me 15, right? That's what the whole thing's out of. If I take 2, let's flip all its bits, I would get 1, 1, 0, 1. Right? That number is 13. 13 plus 2 is 15. Noticing a pattern? It always, no matter which one, I don't care which one you pick this one, right? This is 7, flip the bits, 1, 0, 0, 0. That's 8. 8 plus 7 is 15. So flipping the bits and adding it to the original number adds up to the total possibility that could be out of here. Well, if I want a 9's complement, I got to make sure it adds up to 9. Does that make sense? But that 8 value is way too big. So I would like this to add up to 9. Well, if I took the 8 out and replaced it with another 2, right? Now the total value, if I set all the bits on, is going to be 9. Is that reasonable? All right, now it's not your regular binary code. Agreed. It's not a position value code anymore. However, we can walk through. That's still 0. And that's still 1. This is still 2. That's still 3. Right? I can walk through and build each of these ones up. Right? I could go through and I could say that's still 4. Now my fun part comes when I get to really 4 and bigger. What do I start using? Because I've got multiple ways to do this. Right? I could do 4 this way. I could do it that way. But let's leave this up to 4 here at this point. If I were to flip 4, what would I get? Well, I'd get a 1, 0, 1, 1, right? We agree? Well, this is 0, 1, 2, 3, 4. Well, what is the 9's complement of 4? 5. Right? So I should pick this one to be 5 because that's what I want to get. And I can get it easily now by just flipping bits, which will make it much easier for me when I do calculations if I'm doing it in base 10. Okay? And there are some systems that still deal with base 10 systems that are out there, particularly if you're dealing with small things like a human counter and things like that. Sometimes people like to have ones that just count right in it, odometers and things like that on cars, stuff like that. There's no way they can get an error on them. So that means, right, we get this one by flipping. Well, let's see if that can work nicely here. If I took 3 and I took its 9's complement, 9 minus 3 should be 6. So that should be my next digit in sequence. And if I took this and flipped it, I would get 1, 1, 0, 0. Which is 2 plus 4, 6. So that does indeed make a nice 6 number. So we make that our canonical 6. Even though there's multiple ways to make 6, but this one makes the pattern I want work. So I pick the one that caused me not to change anything in the first half. It's identical to binary in the first half. And the second half I just picked to make it work. Does that make sense? That's all they do with the 2421 codes. The rest of them are exactly the same, right? You just take here 2, its flip should go to 7, right? 9 minus 2, and so you get 1, 1, 0, 1. 2 plus 4 plus 1. Right? There's obviously two ways to make that, but that's the way that works on the pattern, so that's the one we keep. Good? Awesome. So you'll see like the book includes this, but I don't think they really tell you it. It's really there to do rapid calculation of complements if you're doing a BCD system. If you are not doing a BCD system, guess how useful this is? Not really. Right? So it really, there's a lot of specialty codes that get generated in situations, and they're useful for that situation and pretty much not anywhere else. So this is why I say there's just a bajillion codes out there. The biggest thing to me to learn from generating these codes is how do you make design choices to create codes? If you notice, I saw a problem. I said, oh, recognize a pattern. I wanted to add up to 9 because that's what the bit flipping will do for me. I tried to copy binary as long as I could. And the second it got ambiguous or ran into problems, I picked the remaining codes to make the pattern I wanted come out. That's a good general scheme to make a code up. And that maximizes the compatibility between your code and whatever code you're trying to match or convert from. You know, in this case, the most common one's binary. Make sense? So that's a 2421 code. Time-wise considering, I'm just going to do one more. Right? We'll do what's called an excess code. Actually, let me do this on a new sheet of paper. All right. Let's consider our 4-bit numbers again, right? 0, 0, 0, 0, 0, 1, 0, 1. Sometimes. So this is my dyslexia in action. Sometimes I start writing goofy stuff. So I break them into sections. You'll notice I can do, for instance, here, these first 2 columns. Notice they follow that 0, 1, 2, 3 pattern, just like we did before, but there's multiple groups of them. And then within them, I can just copy 0, 1, 1, 0, 1, 1, and just keep repeating that. There's lots of ways to build these. This one is kind of nice later on when we have to build the tables. It'll actually show you how we'll break some stuff up later. So let my dyslexia be something that helps you out. Okay, so right now we count these 0 to 15. That's our standard binary, right? This is 0, this is 15. We've talked about we could use the codes that we want with, say, for instance, 1's complement or 2's complement are different ways to encode minus signs. Okay? Excess codes are another way I can encode minus signs. Excess codes, though, are going to try to answer a different problem, right? So, you know, when I go to 2's complement, this is still 0 through 7, but this is now -1, and this is -8. And it kind of builds, right? So 0, 1, 2, 3, 4, 5, 6, up to 7. Then it goes to -8, -7, -6, -5, all the way up to -1. Right? Now notice that puts all of my negatives on the bigger half of the numbers. So they kind of flip. Right here, there's this big jump of 15 in the negative direction to start the count all over again. Well, what if I don't want to have this flip right in the middle? What if I want them in sequence, constantly getting bigger? Not getting bigger, getting really small, getting bigger again. All right? That makes sense as a desire, that I want them in value order, but I still want negative numbers. So for instance, I could say that I might want to take this sequence and just reorder them. Right? Move these over here and move these up here. I could say minus 8, all the way going to minus 1. And then 0 going all the way up to 7. That make sense? Well, then we got to ask, well, what's the relation, right? This is actually what's called excess 8. I'll show you why in a sec. All right? Just look at these. Take these numbers, and now in your head add 8 to them. All right, 0 through 15. And they went, oh, this is a way I could actually think about storing the numbers. I could take the number I want to store. I could add 8 to it. That resulting number, I look up its binary value and I store that. That is XS8 code. Now 8 is halfway, right? But so's 7, because the real halfway is 7.5. So we usually pick the thing as either 8 or as XS7. In which case, this would be negative 7, and it would go to 0, and then we'd have 1 going to 8 as the numbers we're storing. And then you would add 7 to these to get the value in binary that you store. And the reason is, since the number range goes from 0 to 15, the halfway point is 7.5. So you could either be taking it 7 or 8, and it depends. Do you want to make the negative numbers have 8 and the positive have 7, and then there's 0 sitting in between them? Or do you want the negative to have 7 and the positives to have 8, strictly positives, with 0 in between them? Where do you want to put 0? Right. And you get to decide based on which one you're going to have more of. Does that make sense as a number system? This one actually is used really commonly. When you store an exponent in IEEE double precision or single precision, i.e. when you declare a float or a double, the exponent is stored as an excess number. If it's a single precision, it's XS 127. That's the halfway point. It's an 8-bit number. So, 0 to 255. So it's either 127 or 128. They picked 127. If you do double precision, it's XS 1023 code. Because you got 10 bits, so away you go. Right? So but they store it this way so that when they're doing comparison, the most common thing you'll do is which number is bigger. And so having numbers in ordered sequence makes it faster for them to compare. And so what you want to do is make the common case fast. So they pick the XS code because it doesn't really affect their calculations much, but it sure makes comparisons fast. So they said, yay, we'll do that. Make the thing we do commonly really, really, really quick. So that's really where the XS codes kind of come in. Okay, do we throw comfy? Like I said, you could add just a bajillion codes on top of this. The book includes some more. I might stick a couple in homework. There are some ones that randomly will give you some. Every one that might appear in the homework is pretty much always in the book. You don't actually have to tremendously know the code to do what you have to do with them in there, although there are, it can certainly help. You could also look them up on Wikipedia for all I care, because the reality is, in 15 years, if you have to do this, I guarantee you don't even remember where your book was. You probably look it up on Wikipedia, right? Wikipedia is decent with all the codes, right? Sometimes they give you some really good stuff. Their history may or may not be great, who knows? But they're usually accurate on what happens, so plenty good enough. Okay, that's standard codes. All right. Let's talk about ASCII then. All right. Anybody know what ASCII means? The the American Standard Code for Information Interchange. Stupid facts, right? I don't know why that sticks in my head, like almost nothing I remember, but for some dumb reason, I cannot get that meaning out of my head. And I've tried because it's a dumb piece of information thrown out my head. But that's what it means. Right? It does give you one important thing, which is exactly what the code's problem. It's the code's strength and it's the code's problem. Most computers are built in America, or at least a lot of the design from it, so they optimized it off English characters. Because they said, hey, we're building the things. Because of that, most development tools were written with an underlying system of English. And then there's usually a translation to other languages that's handled in porting to swap the words out. But that means the underlying thinking of the development tools, the compilers and the editors, are almost always developed in English. So if you're going to try to develop and you're somebody from another language, you almost always have to learn English to be able to use the tools. Right? Now, what they said was, hey, look, since we're doing this, now I'm not saying that's right or wrong. That's just a reality of the situation, right? Why they just to let you know why is it there? That's why. Right? And what they said was, hey, we want to take and figure out how do we take English characters and maximize their storage ability. And that's what ASCII is all about, to try to store those efficiently. Now, if you are anything other, and it really is English speakers, right? Because the second you go to other languages, right? If you go to like Turkey and stuff, they have a lot of characters that are similar to us, but they have like the cedillas and stuff like that. If you go to France, they have some extra little fancy characters. You go to Spanish, you have the tildes over them and stuff like that. How do you include that? Let alone what do you do when you go to the Middle East where you got a completely different script, or go to China where you've got, you know, a whole different, you got pictograph type languages, right? How do you handle those areas? Well, now you've got to expand them. So what they did is they made the base part ASCII, and then they made these kind of window pane sections where they would fit the other codes into them and expand it. So they just, whereas we would fit as within a single byte, 7 bits for ASCII, you'll take 2 bytes. If the first byte's all 0, then that code after it is going to be ASCII with its appropriate extended or non-extended code character first. So ASCII gets embedded inside a Unicode. Right? And then everything else is used to fill in all those other characters that you can't otherwise handle, Greek and so on and so forth, to handle the rest of the languages. Does that make sense as where it came from and why? All right. Now, the one thing that ASCII does very nicely, though, and this is something that's worth at least noting, right? The way they built their system was to be efficient. So they're going to break their numbers up. Like we said, think how many characters we have. How many letters in English? 26. I submit to you that we technically, in a sense, have 52, though, right? Capitals and smalls. So we have the lower cases, and we have 26 upper cases. What other symbols might you want to deal with? Okay, or 0 through 9, right? So I can deal with my numbers. So I got 10 of those. Right? We got question mark, right? Period, comma, semicolon, colon, right? All those different punctuation stuff, right? That's going on, right? If you start adding up these, right, there's somewhere around like maybe 10 of those, right? We also have other types of, you know, specialty things that we're going to want to be able to send, like for instance, end of line, right? And things of this sort, right? And other types of codes, right? This is the end of file code. And the most typical way of storing a string of characters is what? Anybody remember? There's 2 ways you could store a string, but there's a really common one everybody deals with. Yeah, it's a character array, but how do you know how many are in there?
As a terminating character.
As a terminating character. What's that terminating character? Yeah, that's because it's called a null terminated array. Right? But I can't use 0 from my numbers. That's why they have you do that /0. It's an escape sequence. You actually need the the digit code is 0. All right, so I can't use the straight numbers as 0, 1, 2 in their standard binary sequence because I also need like a null, right, which is true, all zeros there, right, and so on and so forth. Okay? But I also need a space. That's code 32. Or if you converted 32 into hex, you get 20, right? Which is why if you ever see in your URLs in the web, and they have %20, that's actually the ASCII code. Percent is telling you that it's about to give you a character code, and 20 is the hexadecimal code number for space. So if you ever see those inside your URLs and that, they're just giving you an ASCII code. So it's like all over the place, right? But if you kind of add up all these, there's about 32 of these. When you start adding this all up, you know, we've got over 100 different things we want to put in here. So what they did is they said they'll all fit within 128, which is a nice power of 2. It's 2 to the 7th. Now this, by making this choice, making it small, and they wanted to make it as small as possible, by making that choice, they cut out a lot of special characters. But it gave a big advantage early on, because early machines were really error prone, and so it's going to allow us to add this thing called parity with that extra bit. So we had 2 to the 7th of these characters. Now 2 to the 7th means I need to have a 3-bit binary code and a 4-bit binary code. And we're going to break it up into chunks like this because human beings find it really hard to group things bigger than 5. Okay? And you can just see it. If you drop like, 4, little dots onto a table, you can easily just, you don't even have to count it. You just look at it and say that's 4. You can drop 5 things, you can definitely count 5. When you hit 6, most people have to count them. Okay? So there's kind of a limit, and it seems to be a pretty natural limit within most people. It's somewhere right in that ballpark zone. So what they did to make it easier for the patterns is they split it in half, much like a phone number is split. But they're all going to be treated as one. So this will be our first or our second nibble and our first nibble, and the first nibble has an extra space available to it, which I'll just denote. But the code only needs 7, so that's free. All right, so that's how our setup is going to be. Now, we're going to want to pick, let's say, some other things we want on here. It would be really nice if these patterns were very similar. All right? Such that I could take, it would be ideal if I could just flip 1 bit and go from one to the other. I don't want to, if you say, make this uppercase, you say make this lowercase. I don't want to spend a lot of time looking up and converting things. Anybody ever see in one of the early computers when they're typing? You had no lowercase characters available to you that was on them. So between these two, we're going to make the uppercase characters the ones that happen first. Because on older machines, that's all you had. Okay? So that's some of the sequences on here. The other thing we're going to care about the numbers. I want to keep that binary sequence, right? 0 is all zeros, so on and so forth. But I can't do it for the whole thing because null takes over, right? All zeros. So we're going to encode the numbers in here. It'll fit within 4 bits. We just talked about that with BCD. We'll put the BCD code for your number, and then we'll pick a 3-digit code to tell you you're in the number range. So that way you can just check the first code to see if it is that and then go. Does that make sense as some of the features we'd like to be able to have? All right. And it'd be good to group all these specialty characters together in their own little spot. Right, so we can kind of rule them out really easily, things like that. Okay, since it is stupid to memorize this, I just always bring this chart with me. Right, and you'll see this is the ASCII chart, most significant, least significant. Right, so remember that's my most, and my least has 4. So if I put this in hex, I get a 3-bit, again, octal number, 0 through 7 for the most. And for the least, I've got 4, so that means I can go 16 numbers, which is 0 through 15, 0 through F. So this is just written with the hex, which is a lot easier than just remembering the digits, right? The binary. So you could also do them in this way. And we could look at these. If you notice, for our areas, A, the capitals come before A, the smalls, because this is the most significant bit. The numbers start at column 4 and 5 carries the capitals with some extra stuff. And 6 and 7 carry the same exact sequence except for obviously the stuff. All right? And you'll notice they're similar too in the relations here, right? The square bracket goes to curly, square to curly. So it gives you a nice quick way to get an awful lot of those different codes that you needed. They put the numbers in the column numbered 3, and then they tried to put the other math symbols, less than, equal, greater than, in the same column. So it kind of gave you a nice, easy way to do those checks. All right. Printing special characters like space, 2, 0. Remember we said 20 was the hex code for space. Boom, there you see it. All these ones here are special transmission codes. Null for your null transmit string, start of header, start transmit, end transmit, right? So on and so forth down the line. These are all the specialty code characters. You actually hear these codes spoken out by a machine. If you ever watch an old show where they have like a modem, even now they sometimes have computers beep when they communicate. Well, if you went way back actually when I was young, the only way you could connect, there wasn't even an internet then, the only way you could actually connect to different computers was you had to hook up a modem through your phone. And it would make a beep, and then that beep would get transmitted, right? So you would put the mouthpiece by your transmitter, and your receiver was by the earpiece, and you plug the phone in. And your one would go beep, 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 right? It's making the sounds for these ASCII codes. So if you ever hear those kind of beep, 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 beep types of sounds, they're literally just taking ASCII code and reading them out. And then the same thing would go from the other side, and it would get converted. And these were the codes that told that one what to do. You know, vertical tabs or line feeds, you know, form feed, so on and so forth, carriage return. These are terms you probably deal with in computer science, right? Add a carriage return or a line feed at the end of a line. Well, all of these happens, right? Your escape key. All of those have to have codes that we can specify. And so all of these ones in the first 2 columns are codes. They're what's called a non-printable characters. There is no printing equivalent of these codes. So if you've also ever typed a piece of code, like you cut something from like a PDF, and you pasted it into an editor, and code that's supposed to work that they gave you a printout in the PDF, and you cut and paste it, and the code doesn't work, well, it's quite possible. What Adobe does is to make things look nice, they put in non-printable characters that tell it, they can tell it like vertical tabs or horizontal tabs to shift it one way or another. Okay? So they can kern letters together to make it look prettier, and they do specialized ones for letter combos. When you cut and paste it, you get their codes, not that, but they're non-printable codes, so they can't show. So they're there, but you can't see them. You literally cannot see that they're there. It looks like legit code, it reads like legit code, but there's garbage. So when the machine goes to run it, it sees those garbage characters, and like, I have no idea what you're talking about. Right? That's why never copy from Adobe. Adobe is the devil in this sense, right? They're great to read as long as it's a human being, but don't take code from them because they mess this up badly, right? And so if you understand ASCII, you know exactly what's going on when your code fails. This happens a bunch of times to people when they get to the second half when we do code programming in the labs. So don't let this be you, right? People even copy it from our PDF lab stuff. Don't do that. And that's why we ask you to give us your code, not just a PDF of the lab report. We need the lab report to get your thoughts. But when we want to check that your code works, we can't just cut and paste it out of the PDF. It won't run. You don't want us grading you on that. So that's why we also ask for it. for this same ASCII reason. All right. So let's say, for instance, that I wanted to put something like capital A. Let's say I want to encode capital A and then lowercase r. All right. So to do that, reading on the chart, fairly straightforward. Most significant bit comes first. That's 5. So I've got 5. Oh, sorry. A, 4. There I go, reading in the wrong column. 4 for A, and then 1. All right. That's A. And then I go to R, and it's column 7, and then spot 2, 72. Straightforward, yes? Okay, so you could do that with any code you want. I'm not going to spend a huge amount of time. The biggest thing you need to realize is which one to do first and just get used to it. Okay, that's number 1. The number 2 is, remember, there's that extra little bit here. Now remember, we came from those old days when computers were transmitting by beeps, and somebody mishears a beep, you don't want to change your letter. So because it had to send all these beeps and phone lines are noisy, and you probably hear sometimes even static on your phone lines, how do you clear that up when you've got a bad phone line? Well, one thing you want to do is just know that there's an error that happens. So that's what a parity bit is going to do. A parity bit is going to tell and be able to say, did an error happen? If one single bit flip occurs, it will tell you it's wrong. Won't tell you how to fix it, but it'll tell you it's wrong. And if you know it's wrong, you can just ask, resend that, please. And we can do that a number of times, and however slow we need to do it to guarantee that you get a good message coming across. So the idea of what we call parity bits is very, very helpful. Anybody ever calculate a parity bit before? No? Awesome. Then this will be something new and fun. Okay, let's take our first letter A, which was 41. And we're going to turn this into binary. 4 is 1, 0, 0. Remember, I got 3 bits over here. And here, I've got 4 bits. So 1 in 4 bits is 0, 0, 0, 1. That's capital A in binary for ASCII code. I've got one extra spot here. Parity has 2 varieties, even and odd. Okay? The one we will most commonly deal with is even parity. You could do either. They both work nicely. The biggest advantage that our even parity does is when I'm calculating even parity, I can do it with a single XOR gate. And I've mentioned that XOR gate before. We had dealt with it with the grade codes and that. It turns out the calculation of that only takes 1 gate, an XOR. Now, if you did odd parity, I'd do an XOR and then I'd negate it. I would flip it, right? Because if it's not even, it's odd. But that means I really had to do 2 gates. And that may sound stupid, right, to optimize to that level. But if I can cut the things in half, that's a huge bonus, right? And particularly on something like transmissions, which are notoriously slow, if I can make your transmission circuit significantly faster, that's a big advantage, right? I mean, think on your phone, if I could, send a text or send any other network message in a drastically reduced time, would you want it? Yeah. So we're always about trying to shave things in very efficient ways. So we're going to tend to prefer even. Now what we mean by even or odd parity, it really does mean the numbers even or odd. We're going to count up the number of ones. How many ones occur inside it? And we want the overall total to either be even or odd, including our bit. So since we're doing even parity most of the time, I'm going to just do that one, and obviously odd, you would just do the flip. So if I'm doing even parity, I would count what's here, and I got 2 ones. I'm already even, so I don't want to add any more ones. It would make it odd. So I would just put a 0 in. That's literally all there is to it. There is nothing more to this process. Why this works is, let's say you flipped any bit. I don't care where it is in this sequence. If you're flipping one of these bits, it's either a 0 or a 1 that you flipped. If it was a 0, it becomes a 1. So you have increased the total number of ones by 1, and it goes from even to odd. Does that make sense? So if an error happens when I transmit this number, 41 for my capital A, if any bit flips in here, if it was a 0, it becomes a 1. There's 3 ones now. Odd. But you know you're expecting even, so you know that's wrong. If it flips one of the 1s, it goes to a 0, so you lose a 1. So it goes from 2 to 1, also going to odd. Right? So it doesn't matter whether it's a 0 or a 1 that flips. Either way, it's going to take your nice even total to an odd. Now, if I had done this in odd, I would have put a 1 here to get 3, and that same observation would still work, right? If I flipped a 1, it would become even. If I flipped a 0, it would become even. So that's why either one will work, and this is just easier to build a circuit for. Fair enough? All right, so help me out with R. You guys walk me through what I need to do. I just bumped my head and forgot. What's my first step? Write in binary. What's 7 in binary? 1, 1, 1. What's 2 in binary? 0, 0, 1, 0. Everybody's kind of like, wow, after lunch, right? I get it, it's after lunch. But this is actually a pretty amazingly cool thing, right? If you think about it, I could get an error and I can still get you a truthful message because I go, oops, that was a mistake, and resend. That's kind of a cool thing. This actually is going to build up later in the course. We'll get to where we get to what's called error correcting codes. And it will utilize some of this ideas. We'll be able to, at that point, tell you not just that an error occurred, but where the error was. So you can fix the message on the fly. And it builds off this. But I want to do it in little pieces because I find it's less error prone for you to think about it in that way. So I've got this. I now have my binary. What do I do with that? Okay, how do I know what parity bit to put, right? I got this. So how many ones do I have? 4. So what should I put here? A 0. Why a 0? Because it's even already. And I want even parity. When in doubt, I want even parity. If I want odd parity, I'll tell you. Yeah.
What is like the practical use for odd parities?
What's the
practical use for odd parities?
It's the same exact spot for the evens. The difference is just how do you calculate them when it comes down, which is why I say odd parity is used a little bit less than even is. But in theory, you could use it. The difference in the circuits to calculate this, if you took each of these, the circuit actually looks like you take each of these, imagine all these bits, I take to wires, and I've got a gate called an exclusive OR gate, which looks like that. It's a single gate, and that's the bit I fire up here. So it's one gate for even. For an odd parity, I would add an inverting buffer or a NOT gate afterwards. And that's the whole difference. With this, it's odd. Without that, it's even. So even just allows me to remove that. There is actually a single gate solution that will do it. So exclusive OR is this one. And the extra wings on the side just let you carry extra bits. That's the base thing for XOR. We'll get to this a little more later, but just since you're asking about it. There is another gate that looks like this. It's called equiv that you could build. And you could technically do odd in a single thing. However, there's a ton of things that, I've already started to show you some of the XORs, like the gray code conversion uses XOR. It doesn't use equiv. Right? And it's going to turn out there's just a lot of things that's going to keep using XOR. the more common something's used, people build more of them. And if you build more of them, you build them better. It's just that thing. I mean, what you do a lot of, you just get good at. And so the even parity has really kind of won out because of the fact so many other things used XOR. People just got really good at building XORs. So, yeah.
So if you had a really terrible computer and put the 2 bits, would it still?
No, you flip 2 bits, and it does not. No. Right? Now, there are ways that you can check multiple bits. Right? But you can't just do simple parity. So what we need to do is we need to add, it's going to be what we call increasing the Hamming distance. Pictorially, if you think about this, if you just consider each of these codes, let me just split it down into a small space of 2 bits, right? 0, 1, 0, 1. I'm going to make a little table of possibilities, right? The first bit could be 0 or 1. The second bit could be 0 or 1. Right? What we're doing right now is imagine 0, 0 was a code and 1, 1 was a code. Right? This would be even parity on a single bit. If it was a 0, there's no 1s, so it's fine, so give a second 0. If there's a 1, you need a second 1. So those are your 2 codes. These are the errors. So if you flip a bit, you move to one of these 2 spots, depending on whether you flip the first or the second bit. If you do 2 flips, though, you come here to another code. So if you want to now protect yourself against 2 flips, you got to have more garbage codes in between. So you have to have more space. The number of these kind of walking north